Today we're going to be talking about three different types of continuity. The first thing is we can have a continuous function. So a continuous function is going to look like this. It's just something, bless you, that we can graph without lifting up our pen. So that's just a really quick sketch. That could be like the negative sine curve or something like that, or cosine rather. So a continuous function, though, is something we can trace without picking up. The next thing we can have is a removable discontinuity. Now, a removable discontinuity is going to look like this. It's going to be a function that's continuous, but it might have like an open dot. So this will be an example of removable discontinuity. All I have to do is fill in that dot, and it's continuous. The dot could be somewhere else, too. Maybe the dot's down there. That's still a removable discontinuity. I can make that function continuous simply by moving that dot. Now, a non-removable discontinuity is going to be more complicated. A non-removable discontinuity is going to mean that there's a big gap. So we might have a piecewise function, for example. Maybe we have this kind of parabola, comes in like this, and then it picks back up here. Well, there's a huge gap there. There's no way to quickly make that a continuous function. So therefore, that is called a non-removable discontinuity right here at this C value. Okay, so that's an overall picture of what we're going to be looking at today. So now looking at your actual note, look at the top there, and we have a formal definition of continuity. So the formal definition states that f of c must be defined. That means that we can't have an undefined value at f of c. Also, the limit as x approaches c must exist. And furthermore, that limit that does exist must be equal to the y value. So this is our formal definition to have a continuous function at c. The next part of this says the limit of f of x as x approaches c is L. But if and only if the right-hand limit as x approaches c and the left-hand limit as x approaches c both equal L. So what this is saying is that the limit from the right and the limit from the left have to be equal in order for us to have that general limit. So to find the limit of a continuous function, all we have to do is plug c into the function. It's very easy to find the limit of a continuous function. All right, now, so what did we say about the continuity of a function? It can be one of two things. What is it? Continuous or what? Discontinuous, right? So a function can either be continuous or discontinuous. If the function is discontinuous, that discontinuity can be one of two types. What did we say the two types were? Removable, and what was the other one? Non-removable. Alright, so three types: continuous, removable discontinuity, or non-removable discontinuity. Alright, let's look at this first example. Now, maybe you don't know what this function looks like. I'm hopeful that you do, but if not, all we have to do is graph it on our calculator. So we're going to go to y equals, and we are going to enter the equation. I need parentheses around the entire numerator, divided by the denominator, and then I'm going to do a zoom 6 to have my standard screen. And here's the way the function looks. What did it end up being, that function? It just ended up being a what? Straight line, okay? So if I look at why that happens, I'm going to go to second, trace. Can you see how this is a straight line, but something strange happens at 1. At 1, my function is undefined. What that means is there's a hole in the graph there. So what do you think that means with regards to this function? What happens at 1 is we have a hole in the graph. Why do you think that happened? What did I just do right there? Cross them out, right? So when we have the same factor in the numerator and the denominator, that's going to cause a little hole in the graph right at that point. So this function is y equals 3x with a hole at 1, comma, plug it back into the original, 3 times, or the factored form rather, and canceled form. So 3 times 1 is 3. So there's going to be, we're going to be graphing the line, y equals 3x. So we have a little hole right there. Okay, so this is the way the graph looks. Our line is y equals 3x, but there is a hole in the graph at 1, 3. Now, this notation right here, this is saying the limit as we approach 1 from the left-hand side, from the negative side. So as we get closer and closer to an x value of 1 from that negative side, what's the y value we're approaching? Madison, what is it? What's the y value we're approaching there? 3. And this one is saying the limit as we approach 1 from the positive side. Joe, what's that going to be? 3. Now, as long as these two limits are the same, we said back up here that if the limit from the right is the same as the limit from the left, then we do have a general limit. So this general limit, which has no positive or negative side, is just going to be 3. So we do have a general limit. But f of 1 means what's the y value right there? When x is 1, we don't have a y value. So we have to say right here, f of 1, this is undefined. Our goal with all of this is that I should be able to give you all of this limit information, and based on just knowing that, you should have some idea what the graph looks like. You should know by looking at this that we have a removable discontinuity at x equals 1, just by looking at all of that information there. Questions on that? All right, now let's look at a non-removable discontinuity. So, do we know what this looks like? Does anybody know? Not sure? Okay, if you're not sure, then we can go to the graphing calculator. Let's go to y equals. Maybe you have something in mind as to what it looks like, and hopefully what you're thinking is this. Okay, so some of you kind of have an idea it might be that. Okay, that's the reciprocal function there. We have a vertical asymptote at 1. We have a horizontal asymptote at 0. The function goes way down like this. We don't have to be real super exact. Just kind of an estimate here. And way up like that. Now, following the function, it says when c is 1, find the limit as x approaches 1 from the negative side. So here's 1. The negative side of 1 is here. So we're approaching 1 from the negative side. Where's that y value going, everybody? Down where? What do we call that? Negative infinity. That's going to be called negative infinity. And then the limit as we approach 1 from the positive side. What's that going to be? So what's that going to be? Yeah. So we've got the limit from the left is negative infinity, the limit from the right is positive infinity. In order to have a general limit, these two have to be exactly the same number. First of all, they're not the same, and they're not a number. So they don't meet either requirement, so therefore we say the limit does not exist. So we say the limit does not exist, but we don't say that f of c does not exist. What do we say about the point? The point is, we say that f of c, right here we had the vertical asymptote, so we call this undefined. So is there always a right and left-sided limit? Well, for the examples that we did, there was, right? It doesn't always have to be, though, because we could have a function that doesn't even get started until, like, right there. Then there would be no left-sided limit. So, not always. Most of the time, but not always. All right, we're going to do one more problem today, so let's flip over on the back. We're going to take a look at example 6. This is another one of those functions that we would just really like to know what it looks like. But if you don't know what it looks like, you need to graph it. So we're going to go to y equals. We're going to go to math, over to number. ABS is absolute value. So we want the absolute value of x minus 3 divided by just x minus 3. Do a zoom 6 just to be sure our screen is correct, our window rather. And here's the way it looks. It's always negative 1, and then it jumps up to positive 1. This is another kind of piecewise function here. So we're going to look at the graph, see how the y value is always negative 1. At 3, the y value is undefined. And then at 4, we're back up and it's positive 1. So you've got to be careful with this graph, though. Here's what's going on. It's negative 1, all the way until you get to 3. So you've got to take that all the way over to 3, to an x value of 3. When you get to the x value of 3, you need to jump up, and now you're at positive 1. So we need to see an open dot here and an open dot here at x equals 3. So this is still a function because it passes the vertical line test. It's actually completely undefined there when x equals 3. Both of these are open dots. Now, what about this? The limit is we approach 3 from the left. Jackson, what's that going to be? What's the y value as I get closer and closer to 3 from the left? Negative 1, good. And Michael, what about as we approach 3 from the positive side? From this side? 1, right. To have a general limit, these two have to be the same, and they are not. So therefore, the limit does not exist. What did we say about g of c? What are we going to say about that? Did we say does not exist or undefined? Undefined, right. And then we're asked to discuss the continuity. For this, we would say we have a non-removable discontinuity at x equals 3. Okay? Questions over that? So you should now have enough information to do your homework, so make sure you do that.